Great. So if that's all good, I think maybe I'm ready to pass over to our first speaker of the session, which is Lisa Ibberson from Hitachi Cambridge Laboratory. So pass it over to you. Feel free to share your screen.
Hello, can you hear me? Hello, can everyone hear me? So my name is Lisa Ibberson, and I'm a researcher at the Hitachi Cambridge Laboratory. And before I start, I'd like to just explain that there are 3 children under the age of 10 in the same house as me at the moment. And whilst they've been asked not to interrupt for the duration of my talk, if the last month is anything to go by, that's a bit like waving a red flag to a bull. So if you end up with a demonstration of my terrible parenting in addition to a talk about quantum state readout, apologies in advance. So over the last few days, we've had some excellent demonstrations of talks about a whole range of different quantum information technologies. And for my talk this afternoon, I'd like to focus on just one aspect of a quantum computer, and that is the readout technology. So specifically, I'm going to talk about scalable quantum state readout in solid state systems, with a particular focus on the CMOS compatible silicon systems that we investigate in Cambridge. I'd like to introduce the team at Hitachi, which is headed up by Fernando Gonzalez, and consists of Fernando, myself, Sunye Yang, and James Haig from Hitachi, plus students from the Bristol and Cambridge CDT. And we've been lucky enough to have David Ibberson from the Bristol CDT working with us. And the results that I present towards the end of my talk on dispersive readout in a hybrid system is the direct result of David's PhD research with us. Our student projects cover a range of different topics, from Lawrence's study of nanomechanical resonators to read out the state of silicon CMOS devices, to John's multiplexing experiments and Theo's single spin manipulation in silicon devices. And recently, Giovanni Oakes has joined us to investigate the use of machine learning for automatically tuning 2×n arrays of quantum dots. And I know the next speaker, Natalia, is going to talk in detail about machine learning, which should be an excellent talk, so do stay online for that one. Now, all of our student projects are combined by one thing, which is we all investigate the use of silicon as a host material for quantum computing. And why silicon? Silicon offers extremely long spin coherence times. And in addition, it is compatible with the CMOS industry. And there have been many recent demonstrations of single qubit gates and 2 qubit gate operations in the literature, as well as reports of high fidelity readout. But now, as we think about increasing the number of qubits in the system, we need to think about taking these demonstrations, which are typically fabricated in laboratory scale clean rooms, and somehow scaling them up to a larger number of qubits. And one way of approaching this problem is to modify their fabrication such that it's compatible with the silicon industry. And whilst this is totally possible, it's likely to involve significant optimization of the fabrication processes. In Cambridge, we follow an alternative route. We take devices which are fabricated in a standard silicon commercial foundry, and we modify them such that they demonstrate qubit functionality. And the workhorse of all of our experiments is a device made at the CA Leti fab in France, and it's a split gate nanowire transistor. And it consists of a narrow source drain channel, shown in the top figure in blue, and 2 wraparound top gate electrodes, shown here in a sort of pinky color. And the 2 top gate electrodes are separated by a silicon nitride spacer layer. And if we look at the cross-section image looking between the source and the drain, you can see how the gates shown here in dark grey wrap around the source drain channel. And this leads to a strong confining potential in the top corners of the nanowire channel, which under appropriate bias conditions can lead to the formation of a double quantum dot in those regions. And this wraparound gate structure plus the thin oxide layer can lead to a strong capacitive coupling to the double quantum dot, which, as we'll discuss later, is important for quantum state readout. So how do we use a double quantum dot for quantum computing? Well, we embody our quantum bit in the spin state of an electron confined in one half of the double quantum dot. So here on the left-hand side of the image, we have a single electron and representing the quantum dot. And we use an electron confined in the other half of the quantum dot to read out the state of the first electron. And I think it's easy to see from these cartoons how this geometry could be scaled up from a single double quantum dot to an array or even a grid of double quantum dots in future applications. When we consider quantum state readout, it's important to consider the key requirements. In all quantum computing architectures aiming to achieve fault tolerance require high fidelity quantum state readout. And to implement error correction, this readout must be performed on a timescale which is faster, which is significantly shorter than the coherent time of the qubit. And for us as experimentalists, what this means is we need a large signal to noise ratio in a short integration time. And as we consider scaling up these number of qubits, it's important that any readout architecture has a small physical footprint as well as a viable route to large-scale manufacture. There are several options for performing readout in the solid state. One could position a separate charge sensor adjacent to the double quantum dot, for example, a quantum point contact or a single electron transistor. So in the image shown here, which is from Michelle Simmons' group in Australia, they create a double quantum dot by implanting donors, and they position a single electron transistor adjacent to the double quantum dot. And I think what's particularly impressive for me about this implementation is the small footprints. You can see the 50 nanometer scale bar there, but the small footprint of this implementation, in spite of the fact that it includes a separate charge sensor. And admittedly, at the moment, they're using an off-chip surface mount inductor, which does increase the size of the measurement setup. An alternative to this approach is gate-based readout. So here there's an SEM image showing a surface gate-defined double quantum dot. And one of the gates, which is used to define the quantum dot, is used as a sensor. So it's highlighted in blue here. And this gate-based readout technique has been used by many groups, including our collaborators at UCL in London, who used a multi-module approach to gate-based readout, and together with a Josephson parametric amplifier, achieved a signal-to-noise ratio of 1 in 80 nanoseconds. There exists a third technique, which is appropriate for my presentation this afternoon, which is Cir-QED. And in this case, the electrons in the double quantum dot are coupled to photons in a microwave frequency resonator. So in the image shown on the right-hand side here, the square is a microwave frequency resonator, and it's coupled to a double quantum dot. And using this technique, the researchers at TU Delft achieved an SNR of 6 in 1 microsecond. And my talk is going to discuss how we've combined these last two techniques. So we use a multi-module based system and perform Cir-QED style measurements. I'd like to just look briefly at Cir-QED in a bit more detail. The image on the left is taken from a paper from several years ago, And the meandering line across the top is a half wavelength resonator. And you can see in the bottom left-hand corner, it's coupled to a surface gate-defined double quantum dot. And the researchers recorded the transmitted signal through their resonator and observed a change in the transmitted signal, which is shown in this graph here, as they varied the bias on the double quantum dot. And our ability to distinguish between these two states is determined by the line width of the resonator and the separation produced by the two different states. So I've drawn a cartoon on the right to indicate the condition where the states are easier to identify. So you can see in the cartoon on the right, I've drawn a resonator with a narrower line width, and I've drawn two states separated by this parameter chi. And optimum readout of the states occurs when kappa is approximately equal to chi. And the parameter kappa is determined by the resonator properties, and chi is determined by the electron-photon coupling strength, G. So now I'd like to talk about the setup we've been using in Cambridge recently, this multi-module approach. So we have two substrates. One is a superconducting sapphire substrate shown on the left in blue, and it consists of a superconducting microwave 50 ohm waveguide positioned adjacent to an elongated spiral inductor. And this allows us to inductively couple microwave radiation into the inductor from the waveguide. And the central bond pad of the inductor is connected to one of the top gate electrodes of the nanowire transistor. And what you can see from the SEM image is that the gap between the two top gate electrodes is offset from the center of the nanowire channel. Perhaps that's more clearly shown in the cross-section image on the bottom. And this leads to a larger capacitive coupling between the top gate electrode and the double quantum dot, which leads to a larger value of alpha, the gate coupling factor. We can study the properties of the resonator by measuring the reflected signal with the CMOS device grounded. And we measure a resonant frequency of about 1.88 gigahertz. What's important for quantum state readout is the value of the impedance of the resonator. So the inductor together with the CMOS device form an LC resonator. And we design this such that it has a high impedance. And that together with the high alpha value is important for quantum state readout, as we'll see shortly. To demonstrate that the resonator properties are dependent on the state of the double quantum dot, we vary the biases of the top two electrodes on the nanowire FET. And we observe the classic honeycomb pattern where the numbers in brackets indicate the number of electrons on the double quantum dot. And we look at a particular region of this diagram in more detail, which is indicated by this red square here. So looking now at this small region, we can see that we're looking at the transition between having 7 electrons on the left-hand dot and 11 electrons on the right-hand dot, and 8 electrons on the left-hand dot and 10 electrons on the right-hand dot. And we investigate the behavior of the resonator as we move across this interdot charge transition. So along this line here, the states hybridize, and an electron is free to tunnel between the two. And we measure the resonator response as we move along in the epsilon direction by varying the bias on the VT1 gate. And what we observe is a shift in the resonant frequency as we move across the interdot charge transition. And this shift is given by the parameter chi. And if you remember from our discussion earlier, this chi is the shift between the two states. And chi is given by g squared over delta, where delta is the difference between the frequency of the qubit and the resonator, and g is the coupling strength between the electrons and the photons. And this expression for G is particularly relevant for an experimentalist when designing Cir-QED style measurements. It shows how by tuning and designing our experiment, we can maximize the coupling strength, G. So by operating at a high resonant frequency, by using devices with a high alpha and designing a resonator with a high impedance, we can maximize the coupling strength between the electrons and the photons. We can simulate our experimental results by using the equation for the reflection coefficient. And we find that our simulated data matches or reproduces, sorry, the resonant frequency shift that we saw in our experimental results. So the graph on the right, the plot on the right shows the resonant frequency shift, the theoretical resonant frequency shift. And in addition, the theoretical results simulate the increase in the line width of the resonator as we move across the ICT. And we attribute this increase in line width due to the resonator's interaction with a fairly lossy quantum system. This expression and the simulations allow us to extract some important parameters about our system. For example, a value for the coupling strength, which we obtain 183 megahertz. And we can compare this coupling strength in our hybrid system with that obtained in Delft's fully integrated system. And they obtained a coupling strength of about 175 megahertz. And I think for me, it's particularly interesting that we can obtain a similar coupling strength in this hybrid system as is obtained in the fully integrated setup. To evaluate the performance of our system, we pulse from one region to another of the stability diagram. So from this Coulomb blockaded region marked by the blue cross to the ICT, the Interdot charge transition shown by the orange cross here. And we measure the response of the reflected signal from the resonator in IQ space. And from the two clusters we observe, we can calculate the signal to noise ratio. And we find that we achieve a signal to noise ratio of 3.3 at an integration time of 50 nanoseconds. And we repeat this measurement for a range of different integration times. And by performing a linear fit and extrapolating back to the point where the signal to noise ratio is 1, we determine an expression for the minimum integration time, which for our experiment is 10 nanoseconds. And we can compare this value to the state of the art. For example, Simon Charles, who I mentioned earlier from UCL, who used a JPA to lower the noise floor of his measurement, obtained a T-min of 1 microsecond. And TU Delft, in their fully integrated system, observed a T-min of 160 nanoseconds. So what we find is that our hybrid system obtains the shortest T-min of any silicon system, and it's comparable with the best ever semiconductor system, which was a T-min of 7 nanoseconds obtained in an indium arsenide system. Finally, I'd like to describe how this implementation is compatible with frequency multiplexing measurements, simply by positioning additional spirals along the length of the waveguide. And we've performed a proof of principle experiment of this in Cambridge, where we've been able to measure 2 single-gate nanowire transistors simultaneously at cryogenic temperatures. And for this particular experiment, we measured, we used 2 room temperature microwave sources and combined the signals using room temperature splitters and couplers. And whilst this approach is perfectly fine for sort of measuring 2 or maybe 3 quantum systems, as we move towards larger numbers, I think we really need to think about exploiting the techniques used in software-defined radio, where they use digital signal processing to generate the multi-frequency signal, which they can then up-convert with a mixer by combining the multi-frequency signal with a high frequency reference source. And by way of conclusion, I'd just like to return to our requirements for quantum state readout. This need for a high fidelity measurement in a short integration time with a small footprint and a viable route to manufacture. And I've presented one option for achieving this, our multi-module superconducting hybrid system, which we've used to measure the CMOS devices with a large alpha. And I've described how, using this system, we've managed to achieve the highest signal to noise ratio in silicon for the minimum readout time. That just leaves me really to thank our collaborators, CEA Leti, of course, for making these large alpha silicon devices, the University of Cambridge for fabricating the niobium nitride films, and of course our students, and in particular David Ibberson, for all his work. So thank you also for your attention, and please do ask if you have any questions and I'll do my best to answer them. Thank you very much.
Thank you. That was a really interesting talk and really cool work. So thanks very much. I'll see if we can get some questions in from our viewers, but I'll ask one first, which I was sort of wondering, you mentioned that you use like a standard commercial foundry processor, like at Leti, but then you do some post-fabrication steps after you get the chips back from them. Can you tell us a little bit about that and maybe like how scalable those steps that you do are?
Yeah, I think that's really interesting. And at the moment, and that's part of our motivation. So what we've done is we've kept the two technologies separate. So if you can still see my slides, the red substrate is the silicon CMOS chip, and on the right, it's the niobium nitride on sapphire. And at the moment, we've kept them separately to allow us to optimize both processes. So the fabrication of the CMOS chip is optimized in the foundry at Leti. And we use some very simple optical lithography techniques to pattern the waveguide and the inductor in Cambridge. And you could envisage a point in the future where you could deposit the superconductor on the CMOS chip, but maintaining the flexibility of optimizing them both is beneficial for us at the moment. Also, it allows us to potentially work with different cubic technologies in the future, should we wish to. Okay, yeah, that sounds really cool. I guess, when you said that, I was sort of half expecting you to say that maybe there's some sort of fancy E-beam step, but no, it's really cool to hear that that's, yeah, that it's like quite a straightforward process. The optical lithography is really, yeah, quite simple fabrication technology.
Yeah, cool. So there's some questions coming in now from the viewers. So we have a question from David Shaw, who asks, how comparable is the standard foundry process assumption with the aspiration to improved 2-qubit gate fidelity? So I guess this is sort of saying, your view of using these standard processes, do you see your gate fidelities hitting, these sort of fault tolerant threshold levels? So
we did some estimates of the fidelity for our measurements and obtained about a 99.7% in 300 nanoseconds. I mean, we haven't, these are estimates at the moment, but yeah, we're very encouraged, particularly with these short integration times, that's something that we could hit in future.
Yeah, cool. So I think that also answers another of the questions that we have on here. So I think actually with that, I want to thank you again. And that was really great. And I'm sure there'll be some more discussion over at the Slack channel for your talk.